Okay, as we've reached the half century, I think that's probably a good place to begin. So welcome everybody. Welcome to the Low Surface Brightness Science and Robust Sky Estimation session. My name is Lee Kelvin. I'm a member of the DM team here at Princeton, and I'm joined as a co-host by Sugata Kaviraj, who is the co-chair of the Galaxies Science Collaboration. We have a particularly jam-packed session lined up over the next hour, perhaps somewhat inspired by the Rubin Research Bites on Tuesday. So a particular thanks for all of our speakers preparing their slides in advance, and especially those speakers joining us from time zones where it's not always conducive to public speaking in the early hours. So Sugata and I will begin by giving a general overview to LSB science and how sky estimation impacts that, and then we'll pause for questions before continuing on with the remainder of the session. Before we get into that, as always, just a few friendly reminders. So the code of conduct can be found on the website at this link here. Rubin strives to create a welcoming learning environment, and any discriminatory behavior is not tolerated. So if you do witness anything of that nature, you can find the appropriate reporting structure at the links listed on this webpage here. Also, all talks in this workshop are being recorded, and videos will be posted the next day. We encourage you to submit questions through Slack or indeed through Zoom. And if you do use Slack, you can use thumbs up or +1s to denote questions that you like. And also, please feel free to show your appreciation to any speakers at the end of their talk. And finally, all the session material will be available on the LSB session webpage. So without further ado, I'm going to hand over to Sugata now, who's going to tell us more about the low surface brightness universe, a vast new discovery space for LSST.
Okay, thanks a lot, Lee. Okay, so Lee and I thought it would be worth kicking the session off by outlining the significance of this LSB regime, particularly for members of the audience who might not work in this area. Next slide. So first, it's worth looking at the game-changing depth of LSST, right? So our statistical understanding is obviously predicated on wide area surveys, and it's clear that LSST brings a revolutionary combination of depth and area. So if you look at this figure, around after 2 years, LSST will provide data which is already 3 to 4 mags deeper than SDSS, and of course, when it reaches full depth after 10 years, it will be around 6 mags deeper than the SDSS. So the obvious question is this low surface brightness regime defined as the regime which you can't access using past wide surveys, but is accessible to LSST? Is this regime actually important, right? Why do we care about the LSB regime? And the answer is yes, we do care about it, and it's important because it turns out that actually most astrophysical objects and structures are actually in this regime. So that means that our understanding of how the observable universe evolves is potentially highly incomplete. So next slide, please. So let me give you 3 examples. I'll give you 3 examples of objects and structures that hopefully demonstrate the significance of this LSB regime. So these have an extragalactic flavor to them, but as I'll mention in my last slide, the discovery space for galactic astrophysics is equally large. So if you look at the galaxy population, for instance, it turns out that most galaxies are actually in the LSB regime. So the plot on the left shows effective surface brightness versus stellar mass for local galaxies from a high resolution cosmological simulation. So at 24 mags per arc second squared, the galaxy completeness in SDSS has already dropped to about 10%. Right, so what this means is that while SDSS is certainly complete in massive galaxies, all dwarf galaxies at any kind of cosmological distance, i.e. outside the local group, is invisible in these past surveys. They are, however, accessible in LSST, not just, of course, in the local universe, but out to intermediate and high redshift. And if you look at this in terms of the galaxy mass function, what you find is that if you look at the figure on the right-hand side, what you find is that 85% of galaxies down to say, let's say 10 to the 7 solar masses are actually in the LSB regime. Okay, next slide. So galaxies aside, here are some examples of key structures in the LSB regime, which are also important, critical in fact. So if you think about the theory of galaxy formation, it's predicated on merging, right? But because there are many, many more low mass galaxies as high mass ones, most mergers have low mass ratios, right? So they are sort of minor mergers, as they're called in the literature. And it turns out that the tidal features from these minor mergers are actually very faint. and they are typically fainter than the surface brightness limits of past wide area surveys. But again, they're going to be detectable in LSST. So in the example in the image that I'm showing you, the image on the left-hand side, you can clearly see that the tidal features in the northeast of this galaxy are invisible in SDSS, but they are clearly visible in the HSC, the hypersupreme cam public DR2, which has a similar depth to, let's say, LSST 203 depth data. So to really test our theoretical merger-driven paradigm of galaxy formation, you really need to probe well beyond what is visible in past wide area surveys. And in a similar vein, another key LSB feature is intracluster light. So while galaxy clusters are obviously useful probes of the cosmological model, a significant fraction of the baryons in these clusters actually resides in this diffuse intracluster light, this ICL. So to understand the evolution of clusters, obviously we need to study the evolution of the ICL with redshift, which again requires us to probe well below the surface brightness thresholds of past surveys. Next slide. Okay, so hopefully it's clear that this LSB regime does contain a significant new discovery space, and this discovery space is critical for our understanding of how the universe evolves over time. So while the three examples, as I said before, while the three examples I gave were extragalactic in nature, the discovery space in terms of galactic astrophysics is also equally large in terms of things like, for example, resolved stellar populations, galactic cirrus, et cetera, et cetera. So this really is a new frontier in both observational and theoretical astrophysics. But having said that, there are some important data processing challenges which need to be overcome before LSST can truly achieve its potential in opening up this discovery space. So for example, the pipeline must avoid sky oversubtraction. PSFs, for instance, have to be estimated over fairly large spatial scales, especially for things like ICL. And of course, image artifacts should be removed as well as possible. So we have a fantastic set of talks in this session, which will not only address the significant efforts that are being made in terms of getting the pipeline, the LSST pipeline, ready for LSB science, but also what will be possible using LSST once these pipelines are actually in place. Okay, good. So I'll stop there. Thank you for listening, and I will take your questions after Lee presents his part of the introductory talk. Lee, over to you.
Great, thanks, Sagara. So yeah, as Sagara said, there are lots of data processing issues, and I want to focus on one now, which is sky subtraction in the LSB context. I'm going to tell this through the lens of looking at a recent study that myself, Imran Hassan, and Tony Tyson have submitted for internal review to LSST. So just a quick recap, as Sagara mentioned, LSB source is extremely faint, and as such, very difficult to measure. I've listed a non-exhaustive list here of potential things that can impact LSB science, everything from your choice of observing technique, imaging artifacts, astrophysical contaminants, and indeed how you perform your source extraction. And what I want to focus on for the rest of this section here is sky estimation. So you see here on the right-hand side an image from Mehara et al. 2019 showing hypersuprime cam imaging. And around this particular galaxy, in the original data processing, you can see a lot of flux has been removed. So in this case, quite a lot of the stellar halo has been removed at the sky subtraction step, which is very bad if you're interested in stellar halos. Now, in this case, they were able to resolve this by modifying their technique. So with that in mind, we pose this question: what techniques can we adopt in order to better preserve LSB flux? So what we've done to try and resolve this question is we've created a series of HSC-type simulated images. So we start with two HSC patches, one of relatively low density and one of relatively high density. And we run it through some basic source extraction pipeline using source extractor. Using that information, we create simulated fields that we populate with a range of Sursic models. So for each density region, we construct an exponential field populated purely with exponential type sources. And secondly, another field populated only with de Vaucouleurs type sources. These are the more extended Sursic index of 4 type sources with much broader wings. And into each of these fields, we're injecting about 500,000 sources. So we're going down to an R-band magnitude of about 30th mag. So we're going very faint to ensure that we're capturing everything all the way down to the extragalactic background light. The software and techniques that we're utilizing, we list here. So we're using the source extractor package, kind of top-down thresholding technique that's used very often in the literature. We're using GNU Astro in the noise chisel package. More recent, that's a kind of bottom-up noise analysis package. And we're also using the LSST science pipelines, which is obviously very important here in the context of this meeting, but very useful because it's also used to reduce HSC imaging, so we can directly compare to that too. For source extractor and GNU Astro, we're using 4 different techniques to analyze these data. So we run it in the default mode to get a baseline comparison. We run it in a modified mode. So we change the configuration settings to change things such as detection threshold, the estimation box size for the sky, and so on. We also run it in what we call a dilated masking procedure. So you can see an example of that in the top right here from G et al. That's where you run your image initially through an initial phase of source detection, and then you expand those segmentation maps to try and encompass some of that light that had previously leaked out into the background map and negatively influence the background model. And finally, we also run what we call a model masking procedure. So it's somewhat similar to dilated masking. So you can see an example of that in the lower right corner here. We have an original image, and the segmentation map in the lower left panel here is overlaid in pink. What we do is we opt to fit everything brighter than 25th magnitude with a single SERSIC model. We're not really interested in the core regions of those models. What that does is when we subtract that off, it allows us to remove much of this contaminant flux in the wings, which had formerly entered the sky model. And you can see that when we do that in this example image here, we recover a much lower, much flatter, and more accurate background sky. In addition, for the LSST pipelines, we're running 2 different sky estimation modes. One using a 6-degree polynomial to estimate the sky, and secondly using 128 pixel spline, both options within the DM stack to use that. So moving on to some results. So here I'm showing, using the simulated images that we've constructed, I'm showing the mean estimated sky level using the various software packages and configuration types that I list in the legend here. The software packages are color-coded, so source extractor results in orange, GNU Astro in purple, and the LSST pipelines in black. By column, you have the 2 different density regions, low density on the left, high density on the right. And by row, you have the type of SERSIC sources that we injected. So exponential sources on the top and devocalo sources on the bottom. So there's a number of takeaways from here, and I could talk about this plot for a long time, but I'll try and limit myself. So obviously moving from high density to low density does impact the level down to which you're able to recover a sky estimation map, but gets you about half a magnitude. Changing your source types from devocalo to exponential also gets you about 0.2 magnitudes, about a 20% difference there. Now we start to look at some of the package types, and I want to focus on from source extractor to GNU Astro. So changing from a kind of top-down thresholding to a bottom-up thresholding. That also gets you about another half a magnitude. So just changing your sky estimation type also recovers a much flatter and more accurate sky. And the LSST pipelines lie somewhere intermediate to these 2. So it appears that the bottom-up approach employed by GNU Astro does recover a fainter and more accurate sky. However, I would highlight that the largest gains we find are made in the case of applying model masking to our top-down source extractor approach. You can see here, we're jumping down by almost a magnitude, which is very important because it's something we can apply to the LSST pipelines. It's also something that works well in the era of deep imaging and crowded field photometry. You're not losing as many pixels as you would with, say, perhaps dilated masking. So my final results slide, it's not just about the sky. I also want to very briefly mention the recovered luminosity fractions. So here we're showing the input to the out compared to the output total magnitudes that we recover. On the x-axis, we're showing it for all sources. On the y-axis, it's just for the largest 25 sources. Again, color-coded as it was in the previous slide. So the kind of key takeaways are that GNU Astro appears very well optimized towards recovering these devocalo type sources, recovering about correct magnitude, whereas source extractor and also somewhat the LSST pipelines tend to work better with exponential type sources. If you use the packages elsewhere, for example, using source extractor with the devocalo type sources, you end up missing about 20% of your light in these output catalogs. Conversely, GNU Astro tends to overestimate your flux by about 10% when you're working with these exponential type sources. So there are some caveats there. So with all that in mind, I'll wrap up with my summary. So we've generated a series of simulated HSC regions to try and get further at this issue of sky subtraction. We find that GNU Astro works very well. This kind of bottom-up approach towards detecting signal works very well. However, the largest gains we find are when you apply model masking procedures to these data. So I think I'll end there. Thank you very much. And we're happy to take any questions for both my talk or Sagar's talk for a hot minute.
So Lee, I think this is a clarification from Nushkia. So when you're talking about source extractor and noise chisel, you are essentially doing a comparison between the two, right? You're not using them simultaneously.
That's correct. Yeah, all of these data are processed completely independently of one another. Yeah.
Okay. Ilsang asks, do you know the optical image size for this sky subtraction?
Is that in terms, I'm not sure how to respond to that question. Is that in terms of what kind of sky mesh size we're using? Because it does vary depending on whether we're using a modified setup or a default setup.
Ilsang, do you want to unmute yourself and quickly ask the question yourself?
Okay, so I just wanted to know, is there any sweet spots for you to have either small enough images and give you the robust result? So you're not going to processing the large images from the LSST, right, for the sky subtraction. I'm just curious whether there is any sweet spot in terms of image size.
That's a good question. I mean, the LSST and also HSC, you obviously start with the image size constrained by the size of a CCD. So that's the kind of first level sky estimation is done at that step. With HSC imaging, there's also now a full focal plane sky correction that's occurred. So there are multiple levels. In terms of a sweet spot, that's a lot harder to answer because I think it does kind of depend somewhat on your scientific interest. One person's sweet spot may be different to another. So what we're trying to achieve here is to find something that works best most of the time. But I don't know if there is an absolute sweet spot, if that answers your question.
Okay, let's just take one more. Is it possible to implement noise chisel as part of the default LSST stack processing?
Well, that's a very big question, probably above my pay grade to answer. I think it would require a fair amount of work, perhaps. But I think what we've also shown is there are other techniques that we can adopt, for example, model masking, which achieve similar, if not better results sometime as well. So that's also something we're going to consider.
Okay, let's just quickly take, well, there's one last question on Slack from Michael Strauss. All the recovered sky values in your penultimate plot are positive. An unbiased estimator would give you a sky value at 0 on average, which would suggest that sometimes you have to get slightly negative sky values. I guess the question is that correct?
Yeah, that's the plot I had in mind.
That's a very fair question. So obviously we're showing this is the magnitude axis here.
Right.
So negative values weren't possible to plot. But what we find is when we account for extragalactic background sky, so there's always an undetected EBL component which we don't detect and we're not able to account for. So that pushes your sky levels. They're always going to be positive. When we account for EBL, we do find that our sky levels then fluctuate about 0. But here I'm showing the values inclusive of that EBL, which is mimicking exactly what you do with a real survey.
Okay. Thank you.
Okay, I think we should move on because our time is getting on. Any other questions we will answer either on Slack or perhaps through the Zoom chat. Thanks, Lee.
Yep, thank you all. Very interesting questions. So without further ado, let's move on to Nushkia Chamba, who is going to be speaking about pushing the limits of source detection algorithms towards LSB light. And if you'd like to share your screen, Nushkia.
I'm going to unmute myself first. And then I hope this works. Okay. Do you see my screen?
Yes, we do.
Okay. What screen do you see? The one that's presenter view or?
We see two
slides.
We two
oh,
slides.
okay. Well, I don't know how to, I don't know why that started happening.
Okay. So It's fine as it is right now. We can see it
Okay,
fine.
so I can just, okay, perfect.
Yeah.
Okay, so thank you. I just want to say that this is a work that's actually been led by a group of computer scientists at the University of Groningen. And we are a collaboration of computer scientists and astronomers as part of the Sundial Innovative Training Network. So this is work based on that. So everybody knows source extractor. Lee talked about it as well. It's a widely used program to create segmentation maps. And this is an image of the SDSS showing two interacting galaxies. And overplotted is the segmentation map from source extractor in its default settings. So while it's widely used, we know that it has limits when it comes to detecting low surface brightness outskirts of galaxies, as well as this tidal structure in between. But of course, there are many other tools. So a couple over here. So Lee already talked about noise chisel. There's also Profound, which is a general purpose tool similar to source extractor, and Max-Tree Objects, which is also faint object specialized. All of these tools have some basic characteristics. They all try to measure a background. They have their own background estimator. They all threshold the image with respect to the background and then use that to locate sources. And then they catalog these sources and measure various properties. And this table is a summary of the core methods of each of the tools. I'd just like to highlight a little bit the Max-Tree approach, which is a bit different, mainly that instead of having discrete or set number of thresholds, it's infinite thresholds. So it's a representation of the image at all brightness levels, and it also has the least number of parameters. I'll show you some results about it for all these tools. And so a comparison, we tried to do a comparison of 4 of these tools. And because we're interested in low surface brightness light, we use simulated deep data of the Fornex Deep Survey. This survey goes down to 30 magnitudes per arcsecond squared in surface brightness. And then we basically try to automate the parameters of the tools for this data. And we use 4 different quality measures to do this. And then we test the optimized parameters on real images. So we use images of the Fornex Deep Survey, ISC Stripe 82, as well as a Hubble Ultra Deep Field image. So the ground truth that we used, this is a simulated FDS image example, and we used a ground truth with a very low threshold, which is basically telling you up to what point the source goes undetected. And we did this because we really want to push the limits of the tools to see at what point, to what extent can these tools detect the outskirts of objects and low surface brightness light. For the evaluation, we used a number of scores. So we combined the precision and recall in the detection, and we called it a F-score. It's the harmonic mean of these 2 scores. And we also defined an area score, which basically is the undermerging and overmerging, and it tells you to what extent either a source, which is supposed to be one object, is broken up into many, or the other way about. Many sources that are supposed to be separate, but then they're actually combined into one in the program. And then also 2 combined scores to have a balance between the F-score and the area score. And then for the parameter optimization, what we did was we used 10 FDS simulated images, and we ran a Bayesian optimization scheme on each of the image for each of the quality measures I described earlier. And each of these settings we then tested on the remaining 9 images. So I don't have time to go into all of the exact scores for each of the tools, but what I will talk about is 2 examples of real images from the IC Stripe 82 data set. So this is a deep data set. It goes down to 29.1 magnitudes per arcsecond squared. And on the left is an example of a very diffuse galactic cirrus object, a galactic cirrus, sorry. And on the right is an example of an elliptical galaxy with tidal stream and a bright cluster of bright stars with scattered light. So these are the results. So when source extractor is optimized for F-score, you see that only the centers of the most brightest objects are shown. These are all the colored regions in the image. And when optimized for area score, it does better, but it still misses a lot of the galactic cirrus light. And this is Profound, you have similar behavior here. but more fragments even when you optimize for area in the detection. And noise chisel, it also picks out the galactic cirrus with the area score, but it still misses out some of the structure, but it performs better than source extractor and profound. And finally, with the max-tree object, it picks out almost all of the galactic cirrus structure, and also it performs better compared to F-score in the area score. Here's also an example. The other example, there's a lot going on here as well, but I'll just point you to a couple of things. The first thing is that source extractor, even though you see in some of the panels that the stream is detected, because it's pushing the algorithm, we are pushing it to low surface brightness, it just gives you a lot of false positives. So all of the dots that you see in the background, so the dark regions and then lots of spots, those are all false positives. With noise chisel, it also detects everything, but it fragments the galaxy into very arbitrary pieces. With profound similar behavior, it was too slow for us to optimize it for the combined scores, so we didn't do that. But for the ones that we did, also it fragments the sources. With MT, there's consistent performance, but the issue is sometimes if you have an object which is similar in brightness, it allocates the halo to the wrong object. So that you see it in the F-score. And then I have another example to show you that how the nested objects looks like for MT, which is the max tree. And this is an example showing that you can detect spiral structures if you wish using the max tree, and other algorithms do not have that nested objects approach yet. For background values, we already talked about it. We didn't do such a detailed test, but because we know that the mean background value of the image, of the simulated image, is 0, we tried to see how each algorithm estimates the background of the simulated data. And what we found was that both profound and source extractor consistently overestimated the background. Max-tree underestimated the value a little bit less with the F-score optimization, and noise chisel showed the strongest performance in the background value. So it's compatible with what Lee has found as well. And my concluding remarks is just to tell you how can these results help you. So we have robustly optimized the parameters for 4 detection algorithms, and maybe in the future we can do this also for Scarlet. We didn't consider specific deblending tools, but this is something that we can do. And in our evaluation, we find that both noise chisel and max-tree detects LSP light, with the max-tree overall being more stable and consistent with higher scores, and mainly because there are much less parameters to explore. So noise chisel has 20 parameters, and it's difficult to explore, and you can have many different parameter sets which work very well or equally well. And whereas max-trees has 2 parameters, so it's much easier to explore and automatize. And then also the issues of the fragmentation and different ways of segmenting the sources itself. And the last thing is that I think this would help everyone to be aware and beware of each algorithm's limits and failures, because depending on which algorithm you choose, it depends on what you care about. Do you care about getting the nested sources? Do you care about only the faint outskirts? Do you care about how the halos are assigned to different objects? And also, do you care about deblending? Thank you.
Thank you, Nushkia. And I fully agree with your concluding remarks there. Can I ask Aaron to share screen and get set up while we take questions for Nushkia?
So we have on Zoom chat, which would be the optimized package to identify and remove the brightest sources with?
Sorry, I didn't understand the question. Which is the optimized parameters?
Benny, would you like to unmute and ask the question yourself?
Hi, yeah, so excellent talk. I'm interested in removing the brightest sources in a field, because usually it's very crowded, so that I can actually study the low surface brightness parts. Which one of these would be the best way to go about that? At the moment, I've only used source extractor, but what would be a good one to remove the bright stuff?
Okay. Well, I mean, it depends. So the bright sources also have scattered light. So they also have very diffuse things. So I would, do you have the PSF at hand by any chance? No.
This might be a part of the problem, yes.
Okay, no, I mean, you don't have to, but the thing is that, so I don't want to be pessimistic, okay? But going through all these algorithms, there's not really one perfect one. So like, max trees is great because it's almost completely automatic. You can run it, it's fast, and it's only 2 parameters, and it gives you a very nice, easy way of seeing how the image looks like, right? But the thing is that when the moment you go to very, very low surface brightness, it starts connecting objects through the noise. So you cannot really, it happens also with noise drizzle. If once you push the algorithm, if you have, so I think I don't know if I want to share my screen again, but in my slides there, you see the example with the galaxy close to the stars, and it starts connecting them. And that's something that I'm actually not even sure how to disconnect. Maybe deblending can help. So I want to look at Scarlet more, whether it can do this. But I would say like the easiest to learn and use is MaxTree, because you only have 2 parameters, and it's great. It's on GitHub. I can send you the link.
Oh, yes, please.
Yes, sure, no problem. Whereas many of the other tools, it's like, I mean, it's really a nightmare when you have to manually tune parameters. I gave up. And so this is one of the reasons why we did this project, because we wanted to see whether we can automatically parameterize, and you can. But the thing is that once you have so many parameters, you can have many different optimal quote unquote parameters which work similarly. So then how do you choose? I mean, it's, so you need more, we have to do maybe more tests, but it's not clear. And anyway.
Thank you so much, Nushki. I think
No
we need to
problem.
move on.
Brilliant.
Sorry.
But thank you again. Please share your applause on Slack. So without further ado, we'll move on to Aaron Watkins, who's going to be telling us about testing the current LSST DM stack sky subtraction.
Yes, hello. So as mentioned, I'm going to be going over some testing that we did using model galaxies regarding the current implementation of the sky subtraction. We've been doing this in conjunction with the DM team over in Princeton. Let me just get right to it. The basic strategy here was we wanted to quantify the impacts of the current sky subtraction implementation regarding low surface brightness science and also just galaxy science in general. So we did this by using model single surface component galaxies, which are easy to measure and quantify. And we sent these to the DM team, who injected them into the pipeline at the COAD stage. So everything that I'm going to be showing you in this talk is the final step in the sky subtraction, this very localized one that seems to be mainly to help out the deblender. So that'll be worth keeping in mind as I proceed. This does not include any of the chip-to-chip or full focal plane sky subtraction. So it's sort of the PDR2 version. Let me start with a quick visualization. On the left, you can see one of the model galaxies that we input. This is a low Cercic index galaxy. And on the right is the same galaxy after the final sky subtraction step was implemented. So you can see right away these dark arcs below and above this model galaxy, which is caused by an over subtraction from this last sky subtraction step. If we want to quantify this, this is showing radial profiles of a different model galaxy, not the one that I just showed, but one with a higher Cercic index. On the left, I'm showing surface brightness profile. The blue curve is the input model, so this is measured directly off of the image of the model galaxy. The black curve is the measured off of the image of the model galaxy after sky subtraction. The lower left plot is showing the difference between the blue and the black curve. So you can see immediately that starting at around 26 megs per square arc second, in this case in the I band, we've already got something like half a magnitude over subtraction, and it gets much worse at lower surface brightness. This also has an impact on the total magnitude, which you can see in the right plot. This is the curve of growth, which is the cumulative sum of the flux of the galaxy as a function of radius converted to a magnitude. Again, blue is the input model, black is post sky subtraction. The central right panel is the difference between the blue and the black, and then the bottom I'm just showing that as a flux fraction loss. So if you take the final point in that central panel, this is essentially the difference between the total flux in the input versus what happens after the sky subtraction, and you can see that we've lost about 1.2 magnitudes worth of flux due to this effect. So this is just showing the I band. The effect is fairly similar in the other bands, but there are slight differences which end up leading to color gradients at low surface brightness, and that's what I'm showing right here. I should note that the average colors, the integrated colors, are not very much affected, but when you get to lower surface brightnesses in the outskirts, you do start to see these subtle differences in the sky subtraction from band to band, leading to very different measures of the color, so upwards of half a magnitude in some cases. Whichever over subtraction in whichever band is more severe is what causes the color to either turn upward, redward, or turn blueward, which is why you see this different behavior in these different colors I'm plotting here. We also wanted to explicitly test the impact of the object's surface brightness and also the object's size. That's what I'm showing in these two plots. On the left, this is an array of model galaxies, all with low Cercic index 0.3 and identical effective radius, but changing central surface brightness, which is on the x-axis. The y-axis here is the total aperture magnitude of the model measured off the image, subtracting the input catalog value. So a value of 0 is what you want, a positive number is an over subtraction. And you can see that it's over subtracted a little bit at all magnitudes, but particularly below this 26 magnitude per square arc second. Again, we're getting systematically very severe over subtraction. On the right, I'm showing the impact of size. These are all, again, identical galaxies, same Cercic index, central surface brightness now with 21, but changing effective radius. And you can see that at about 7.5 arc seconds effective radius, we've got, again, a systematic over subtraction, with the larger objects being subtracted more severely than the smaller objects. So this is both impacting LSB things and also large angular sized HSB things. The latter problem seems to be more severe, which is what I'm showing here. These are, on the left, I'm showing surface brightness profiles of the largest of the galaxies in that previous sample. Again, central surface brightness about 21. The black is the input model galaxy and the red is post-sky subtraction. And again, the lower left plot is the difference between the black and the red. And here you can see that there's actually systematic over subtraction at all radii. And at low surface brightness, the effect is incredibly severe, even compared to what I was showing before. We're at about 24 magnitudes per square arc second in the black curve. The red curve is below that by something like 5 magnitudes already. But some good news is, if you look at the right plot, this is the smallest galaxy in that previous sample. Again, central surface brightness of 21. And here you can barely see the difference between the two curves. If you look at the lower plot, it seems like the sky is being over subtracted only noticeably at somewhere around 29, 30, 31 mags per square arc second. And even then, it's only by about 1/10 of a magnitude. So the large angular sized galaxy is very badly affected, but small high surface brightness objects are not. So how does this impact our science? So Sugata showed this plot already. I probably don't need to explain it. If we take that 26 mags per square arc second limit from our surface brightness tests, then we just draw a line on there. You can see that that means any survey of dwarf galaxies in the local universe is only going to be complete down to about maybe 10 to the 8.5 solar masses. Obviously, you want to get to lower surface brightnesses to see the rest of the population. At higher redshifts, when you start getting into things like surface brightness dimming, of course, this effect is going to be substantially worse. This also impacts ICL pretty severely. You'll hear a lot more about ICL in the following 3 talks, I believe. But it's a good measure of cluster evolution, particularly if you observe high ICL at high redshift, greater than 1, which is technically something LSST is capable of doing. But again, if you look at the central bottom plot, if you just draw a line at that 26 mags per square arc second limit, we're not even in the ICL regime in that case in these clusters. You usually don't start to see ICL take over the radial profiles until something like 28 to 30 mags per square arc second. And this is optimistic because ICL is a large angular sized object typically, so that effect will also come into play, and you might even be getting over subtraction starting at much higher surface brightnesses So the basic takeaway here is that with this final implementation of the sky subtraction in the stack, you just cannot do ICL science with it. So how do we fix this? What's one possible option for remedying this situation? We've done some preliminary looking into the PDR2, Sugata also mentioned this. And in fact, in PDR2 and HSC, you can find LSB structures at 27, 28 mags per square arc second around nearby galaxies, tidal features, and other things. It seems like it's not doing quite so badly there. So this leads to an option of a possible bifurcation of the pipeline. We might have PDR2 or more likely some modification of PDR2 that's optimized specifically for LSB science on the one branch. And then the second branch uses this final more localized sky subtraction to help out with the deep blending and the weak lensing science. So our next step is we're going to test the PDR2 sky subtraction in much the same way as I just described. We tested this sky subtraction. We've been injecting galaxies into the raw images and are processing them through the full data reduction procedure. And we're going to go ahead and see how that affects these models as well. So I think I'm out of time, so maybe I'll just leave this up and take questions.
Thank you so much, Aaron. Can I ask for Christina to set up a share screen while we take maybe one quick question?
Okay.
So I'm not sure who this question is for. There's a question on Slack. For a given data release, is the overall plan to report corrected magnitudes for each object, or else to report the biases as a function of magnitude generally? If the former, would such corrections be by environment? So for example, as a function of the sky position.
That doesn't sound like a question for me.
No, I don't think so. I think it might be more for someone from the pipeline DM team, perhaps. Maybe we can leave that one till later.
Yeah, perhaps we'll save that one. And please,
Okay.
anybody who wishes to submit a question for Aaron, please do so on Slack. But I think we should probably move on.
Okay.
So next up, we have Cristina Martinez-Lombia, who will be speaking about how much ICL will the Vera-Rubin telescope reveal. And if you're able to share your screen, Cristina.
Hi, I'm trying to. Give me a second. Can you see anything?
No, we can just see your video at the moment.
Okay, I don't know why.
Yeah, there we
Okay.
go.
Right. So, what you are seeing?
Yeah, we can
You're
see the presenter notes.
Oh,
as
okay.
well.
Yeah,
There we go. That's better.
perfect.
Okay. So, thank you so much for giving me the opportunity of showing my result here. I try to do my best, but it's 5:30 a.m. here in Sydney. So I'm currently a postdoc at the UNSW working with Sarah Brove and Mireia Montes, and I just started a few months ago. So my first task here was to check whether it is going to be possible or not to detect intracluster light with the Vera-Rubin telescope data. We wanted to have an idea of what kind of data or studies are we going to be able to perform, and if is there anything we can contribute in order to improve those the pipelines to not to remove the loss of brightness stuff. But first of all, what is the intracluster light, or BCG? It is basically the diffuse light that spreads across the center of the galaxy clusters. It is usually concentrated around the brightest cluster galaxy, or BCG, and it comes from stars that are ripped out from their host galaxy due to interactions. The other main question here is why is the ICL important? As I just said, the ICL is formed due to interactions between the galaxies in a cluster. So it can be seen as a record of the mass assembly history of galaxy clusters, and also as a record of the interaction that the BCG has undergone over its lifetime. Usually when simulations of BCG growth consider that a percentage of the stars that are supposed to merge in the BCG, they actually end up in the ICL component, they reach a better agreement with observations. So, however, as all the laws of brightness stuff, this is very faint and hard to detect. So we have actually very limited works about it with very limited samples. And if we plot a radius of brightness profile from the center of the galaxy, like as you can see here on the left, the ICL can usually be detected below 26 magnitudes per arc square, and it appears as an extra component on top of the BCG. This different component can also be detected from the ellipticity of the light as it increases with radius, and also from spectroscopic studies, as you can see in the image of on the right, that have found that the velocity dispersion at a large radius increased to reach the velocity dispersion of the cluster, of the galaxies of the cluster. So this light seems not to be bound to any galaxy in particular, but to the potential of the cluster. This is also in agreement with results from simulation, where the more extended component is the one showing the higher velocity dispersion. All this together made the ICL a very important and a very interesting feature, but I don't have to go through all this stuff. So if you want to know a bit more, just take a look on this very nice review that Mireia did last year. So in order to have an estimation of how much ICL are we going to have in the LSST data, we decided to take image of gamma groups from the LSST science platform. And in particular, we choose the HSC data that it's being reprocessed every 2 weeks. We pick up the gamma 15 field of view, and in particular, the data that fall within the track 9615, which is the one that is being reprocessed. Our first idea was to take all the gamma groups that fall within that selected area. However, when I started to take a look on the images, we saw that there was a very clear oversubtraction around the big galaxies, such as those that you can see in the image, where it is pretty obvious actually that the outer parts of the galaxy, between the outer spiral arms, there has been an aggressive oversubtraction, an aggressive subtraction from the background. Smaller galaxies also suffer this effect, but to a lesser extent. Obviously, we immediately reject this first idea and try to figure out what to do. So, inspired by this work from San Juan and collaborators, where they found that galaxy clusters seem to be less affected by background issues when going to higher redshift, we decided to pick up a few gamma groups at higher redshift, not too high, but at higher redshift, the higher that we have. Sorry. However, here you can see that in the image, we still see some oversubtraction around the BCG, which was pretty bad news, but we decided to continue anyway to see what was going on and if we could do anything with it. So we studied a couple of gamma groups. Here I'm going to show you one of them, a redshift 0.336, but I have to say that we found pretty much the same for the other groups. So let's take a look on the software brightness profile on the left that was obtained with the elliptical apertures on the right. Note that we have combined the GR and I bands in order to increase our signal to noise in our test. But as you can see in the profile, it completely falls when reaching around 35 kiloparsecs. 35 pixels. Our plotter, there is a sourcing fitting by performed by the gamma group to this particular group. As I said at the beginning, the ICL is supposed to be an extra component on top of the BCG, but here we are seeing basically the opposite behavior, which is something in quite good agreement with what Aaron just showed in the previous talk. This, as you can guess, is due to sky oversubtraction. It is very important to note that those 35 pixels for this cluster at 0.3 redshift are actually just 40 kiloparsec. So basically, we are not even getting out of the BCG halo when we can no longer detect any feature. And actually, the ACL has 100 of kiloparsec of physical scales. This over subtraction is also very clear when looking at the ellipticity, the position angle, and the signal to noise. Also, in principle, the ellipticity seems to have the expected behavior. This is that it increases with radial. Then at the same position than in the profile that I just showed to you, the fit stops and basically it cannot fit any feature anymore. The same happens with the position angle, and if you take a look to the signal to noise values on the right, we find the same kind of agreement as the values drop just after that 40 kiloparsec. So going back to the initial question of how much ICL will the Raman telescope reveal, the short answer would be that nothing, unless of course we do something to improve this issue in the pipelines. One of them could be not to perform a small scale background subtraction, which I think is being addressed for the next data release, but I don't know it in detail. Maybe some of you will know for sure. And another possibility is to recover the sky that has been removed and then perform our own stuff. But this implies more work, of course. And here my question is that when doing this in the LSP, something which in principle is possible, are we recovering all the removed background, or is there any missing component? Because this is not very clear for me. So I finished here. I just wanted to say that in the Laws of Awareness Challenge 3, we are happy to contribute to any possible solution to these issues. Thank you so much.
Thank you so much, Christina. Some lovely work and some really important takeaways there. So can I ask Mireia if she would mind sharing her screen while we take perhaps a quick question for Christina?
Okay, I'll stop sharing.
Robert, would you like to just clarify? I think you have a question about exactly which data product this is that Christina is showing. Is that right?
Well, more to the point that those massive over subtractions would be changed in the code a long time ago. So when you're thinking about LSST data, ribbon data, you shouldn't expect to see over subtraction to 24th magnitude. As I think we demonstrated, you could get down to something like 28, 29 megs per square arc second. There were common and bad side effects. Yusra, who knows more about this in detail than I do, suggests that maybe you're looking at the wrong data product, because we do generate a strongly sky subtracted data product for doing faint object analysis. So I'd suggest Yusra.
So what would be the correct data product?
I guess my question was, were you plotting the deep coad or the deep coad calyx?
The deep coad calyx.
Okay, that's the data product that has had the very aggressive 128 pixel spline pixel bin spline applied to it. The deep coad data product is the one that has the full focal plane background subtraction applied to it.
So do you mean that if trying with the deep coad, just deep coad, this is not going to be that aggressive? Because I did some tests in the LSP and it wasn't too different. So maybe I did something wrong, or?
Can I suggest, in the interest of time, maybe we can add this to Slack, if that's okay? And we can document their responses. Okay, I think we unfortunately need to move on. So we have two Sparkler talks to round off the session. So first we're going to hear from Mireia Montes, who's going to tell us about the intercoastal light of Abel 85. Over to you, Mireia.
Okay, can you see the screen?
Yep, looks good.
Yeah, perfect. Okay. So hi, everybody. My name is Mireia Montes. I'm a postdoc at the University of New South Wales, and I'm working with Sarah Braff and with Christina. So today I'm very briefly going to tell you about my recent work using the hypersupreme CAM observations to study the intercluster light of this cluster, about 85. So we have seen that the HSC pipeline is not doing a great work at preserving the intercluster light, and it is even worse when we study nearby clusters. For this reason, and mainly because I'm very stubborn, I have processed the data of this cluster, Abel 85, myself in order to study the intercluster light. So the whole data process is quite long, so I'm just gonna focus on the more low-surface brightness dedicated steps. So the goal, as the intercluster light is faint and extended, is to achieve the flattest background that we can. So we don't want any gradients. So for example, one of the steps that can introduce gradients in our data is the flat field correction. So as we don't want to introduce gradients, so instead of using the twilight or dome flats that can, they can put some gradients into our images, we decided to derive our own sky flats. However, we realized that the rotation of the instrument has some effect on those flats. So we derived two different flats, one with the same rotation as our science images, and one that has a random rotation. And we see that when compare both of them, we can see a gradient of like around 1% across the CCD. And that has an effect on the science images when we go into the whole processing. This is the final image using both flats. The one in the left is the flat with a random rotation, and the image on the right has the same rotation as the science image. You can see that you can see some residuals on the image on the left. So it's something that we have to take into account. Another step that we should be very careful is the sky subtraction. So the thing is that this cluster is very extended in the sky. So the intercluster light is very extended in the sky. So any kind of sky subtraction that is not dedicated to preserving the intercluster light, it's not going to be good enough for us. So even though if like the HSC images they don't look like that anymore, we have to do our own thing. So we've been very, very conservative, and we just subtracted a constant to each of the mosaics that went into the final coat. Another step is taking care about the stars, the very bright and not that very bright stars in our field of view. That can contaminate, their wings can contaminate the photometry of the intercluster light. So we model the stars of the stars in our images. We subtracted them, as you can see here in the middle, and then we basically mask everything that is not basically intercluster light or BCG. So this is the final result. We have two images in the G and the I band, and they're around like 30 minutes each. So here we can see the G band image as the background, and some insets of the image that are like the BCG and another galaxy in the field of view. So now with the images ready, we can explore the intercluster light. We have used ellipse to see how the ellipticity increases with radius, assigned that the intercluster light stars are linked to the distribution of the cluster rather than that of the galaxy. And we have also derived the color profiles with that show three different regions. The inner part is it's an indication of the core of the galaxy. It's a core that is already known. We see also the middle part that it's like a typical color gradient of elliptical galaxies. And this outer part from 70 kiloparsecs to 200, more or less, that it's flat. It's again a flat gradient, or flattish gradient, that indicates that there are some mixing of the stellar populations, which is a consequence of the mergers with the BCG. If we take the average of this color, we can infer that the origin of this light at a large radius are galaxies of around 10 to the 10 solar masses, which is something that we've already seen in results of massive clusters in other works. And the last thing I want to mention is that if you want to learn more about intercluster light, you should sign for the low surface brightness working group data challenge number 3. And if you want to know more about these challenges, you should ask Sarah Braff. Thank you.
Thank you so much, Maria. Please share your applause on Slack. Can I ask Yuan to set up our last talk while we take a question for Maria?
So there are no questions at the moment, either on Zoom or on Slack.
Okay, everyone's thinking about it. So please post your questions on Slack if you have any questions for Maria. And let's move on to our final talk of the session. Yuan Zhang speaking about studies of intercluster light through stacking dark energy survey data. Over to you.
Can you see my slide okay?
Yeah, looks good.
Great. So I'm going to talk about how we study intercluster light using a stacking method with the dark energy survey data. So here the background image shows one galaxy cluster in DAS data. It is located at redshift 0.23 and has a richness 5.7. So it's a relatively massive cluster. So we take images like these clusters, and then this, in our work, these images first go through the official DS data processing pipeline. In this pipeline, they are corrected for bias and flats, and also there is a global background subtraction step, which means there is a background that is estimated for the whole field of view of 3 degree squares, and they are subtracted from all of the images of each cluster. And after these images are derived, we co-add together them and then mask out the objects that are detected in these clusters so that we can look at low surface brightness features. So I admit that, with the official data processing pipeline, the images are definitely not perfect for detecting intracluster light. Like, there's still residual light from bright stars, bright galaxies, and also sometimes uneven flux levels created by uneven sky subtractions. So in my method, I use a stacking method or averaging method that I would stack or average the measurements of several hundreds of galaxy clusters at the same time. So the end result is that you would have a relatively smooth measurement of the intracluster light of several hundreds of clusters. And any features that are not related to the clusters will hopefully be removed in this kind of stacking averaging step. And even after that, the result is still not as perfect as I had hoped for intracluster light detection. So there is a final background subtraction step. And in this step, we stack together the measurements, the flux measurements of several thousands of random points that are scattered in a DS footprint. So here I am showing the surface brightness measurements of galaxy clusters and also the surface brightness measurements of random points. So galaxy clusters are in black and random points are in red. So the random point profile measurement is the background level that we want to subtract next. And there are two things you should note here. First, their flux level is negative. So that means in the previous sky background subtraction, we have overall over subtracted the skies for all of the images in DAS data. So that needs to be corrected for. And then the second thing is that there is a radial dependence of the random point background levels. That means the background level is lower in the center of clusters and higher towards the outskirts of clusters, which really plagued us for quite a long time. So eventually we came up with an explanation. The explanation is that, there are very bright stars like Tycho stars or very bright nearby galaxies in the sky. And we do not tend to find galaxy clusters near these very bright objects. So galaxy clusters tend to exist at a distance away from these very bright objects, But meanwhile, because of the extended PSF, these bright objects would still contribute some residual background to the galaxy clusters. And the contribution is lower when you are a bit further away from bright objects, and a bit higher when you are a bit nearer to them. So the background level is lower in the centers of galaxy clusters and higher towards the outskirts. And that would affect measurements if you want to go as deeper as 31 magnitude per arcsecond squares. So eventually that is another background that we wanted to subtract off. And you can see that the good thing is that the background level of the random points in the clusters do converge at a very large radius, so that we are happy about. And with that, here I'm showing my measurements of the intracluster light at redshift 0.23 by averaging 300 clusters. And thanks to Erin for already showing that. We have detected intracluster light out to about 1 megaparsec from the cluster center. And it does turn out to be, a quite significant component of galaxy clusters. So I will just skip the rest of the results, but I want to point out that based on the detection and measurement, we have done quite a bit of works on the intracluster light properties, including comparing the intracluster light radial distribution to lensing and see if you can use intracluster light to infer cluster masses. And we also stacked diffuse light around luminous red galaxies, which turns out to be quite different from intracluster light. So if you want to know any more about any of this work, please let me know. I also want to say that I'm very open to results comparison and collaboration. So if you want to compare your results to ours, I would really appreciate it if you can let us know, and I will send you our results or even code. So thank you.
Thank you so much, Roman. Great stuff. Please share your applause on Slack. So we have time for a question, I think, if anybody has anything. I know there's a lot of discussion ongoing. It's been a jam-packed session on Slack and indeed Zoom. Okay, well, if there's nothing forthcoming, I'm sure people are thinking about a lot of things, so please feel free to share questions on Slack. And I think there's a lot of questions that have been popping up in the Zoom chat as well. When this session finishes, that chat will disappear. So if there's anything that hasn't been answered, please feel free to copy it across. So thank you again, and indeed thank you all of our speakers. It's been a really fascinating session. It's great to see so much work going on. LSB science will be such an important topic for LSST and Rubin Observatory. There will be future forums where we'll discuss this further. I think Sagata mentioned the Galaxies Science Collaboration has regular telecons, and also the LSB working group within GSC has also been running a number of LSB data challenges. So there'll be further discussion and work there. So thank you again to all our speakers. Thank you for everyone who participated in the Q&A. And I look forward to seeing you at a future meeting. All the best.